You've probably come to realize by now that mathematicians are pretty good at pulling rabbits out of hats. But rather than doing conjuring tricks with rabbits, today we're going to look at a problem involving rabbits, one which has intrigued mathematicians for hundreds of years. At the beginning of the 13th century, the Italian mathematician Fibonacci posed this rather interesting problem. He proposed that rabbits breed in the following rather unlikely way. A pair of rabbits in its first month of life produces no young, but at the end of the second and each subsequent month, they produce a new pair. Starting with just one pair, how many pairs will there be after 12 months? Actually, we're going to be a bit more ambitious and to ask a general question. Can we find a formula which gives the number of pairs of rabbits at any time after the colony begins? In order to solve this problem, we're going to call on many of the techniques you've learned in this block. We'll be using networks and the theory of matrices. And in particular, we're going to use the QDQ to the minus 1 decomposition and the computation of powers of matrices. But before we can see how all that fits in, first of all, we've got to make quite sure that we understand the problem. So what I'm going to do now is to carry out a simulation. Here I've got a number of pens in which we can keep track of what's happening month by month. And the first rule is that we begin the first month with just one newly born pair of baby bunnies. The second rule is that each pair becomes adult after 1 month. So in month 2, these babies have become adults. So now they're adults, they can produce babies of their own. And the third rule we use is that each adult pair produces a pair of babies at the end of each month in which they're adults. So in the third month, we shall have a new pair of babies. And of course, we'll still have our original pair of rabbits. Throughout this process, we're assuming that none of the rabbits die. And so now the process continues in much the same way, using these same rules. At the end of the month, this pair of adults will produce yet a further pair of babies. This pair of babies will have become adults, and we still have this pair of adults. In the next month, now both of these pairs will have babies. This pair will have become adults, and we still have these two pairs of adults. Let's just see what happens for one more month. In the next month, since we have 3 adult pairs here, we're going to have 3 pairs of babies. How many adults will we have? These 2 pairs of babies will have become adults, and we'll still have these 3 pairs, which makes 5 altogether. And so altogether, we're going to have 3 plus 5 is 8 pairs of rabbits. Now, we've actually recorded the numbers of rabbit pairs that we had in each month, so that we can look back and see how the population's been growing. Remember, it's the totals that we're really interested in. But notice how the same number sequence seems to crop up in each row. And that's something that you can see very clearly if you represent the process as a network. Well, here's the situation that we had in month 6. We have 5 adult pairs and 3 baby pairs, making a total of 8. Now let's trace it through to the next month, the 7th one. Now these 5 adult pairs and 3 baby pairs together combine to give us the number of adult pairs in the 7th month, and that's 8. That's just the same as the total number of pairs of rabbits we had in the previous month. How many baby pairs are there in the 7th month? Well, we have as many pairs of babies in the 7th month as we had pairs of adults in the previous month. And so the total now is 13. Let's carry the process on for one further month. So the number of adult pairs in the 8th month comes from the pairs of adults and babies in the previous month, 13. And the number of babies comes from that single path, and that gives us 8, and a total of 21. Now we're interested really in trying to find a general formula for the total number of rabbit pairs in each month. So let's look at what happens in the nth month, and think about what happens when we go from the nth to the n plus first, and then to the n plus second month. Let's have a symbol for the total number of rabbit pairs in the nth month. We'll call it an. Then the total number of rabbit pairs in the n plus first month is an plus 1, and in the n plus second month it's an plus 2. From what we know about the process, we can now fill in the numbers of adult and baby pairs. For example, the number of adult pairs in the n plus first month is equal to the total number of rabbit pairs in the previous month. So that's an. And similarly, the number of adult pairs in the n plus second month is an plus 1. And in the nth month, it's an minus 1. The number of baby pairs in the n plus second month is equal to the number of adult pairs in the previous month. And that's an. And so in the n plus first month, it's an minus 1. And that tells us the whole story. Because what we see from this is that it actually gives us a formula for the total number of pairs in the n plus first month in terms of the total numbers in preceding months. An plus 1 is equal to an plus an minus 1. This formula reduces the calculation of the number of pairs of rabbits month by month to simple addition. We start off with a1 equals 1 because we started off with just one pair of babies. And a2 equals 1 because in month 2 there's just one pair of adults. And so from these two starting values we can continue to use the formula. a3 is equal to a2 plus a1, that's 2. a4 is 3. And in this way we can continue to generate the sequence of numbers. It's known as the Fibonacci sequence.
So now we've got a formula which enables us to calculate an if we know the previous terms. But what we'd really like is a formula for an all by itself. Our network suggests that we try and bring in matrices. But in order to do this, we need to put numbers in the network. Well, I've put 3 1s here. And the reason is that an plus 1 is equal to 1 times an plus 1 times an minus 1. And an is equal to 1 times an. Well, we can represent this situation by a column matrix, like this. And similarly, this column matrix represents the situation in the following month. So each of these column matrices represents a pair of successive Fibonacci numbers. Now, if we want to represent the change in the situation from this to this, then we can do it by multiplying by a 2 by 2 matrix. What are the entries in this matrix? Well, we can find them in the same kind of way as we found those in the network. an plus 1 is 1 times an plus 1 times an minus 1. So we have 1 and 1 in the top row. And similarly, an is 1 times an plus 0 times an minus 1. So we have a 1 and a 0 in the bottom row. Let's check how this works in a particular case. For example, if n equals 4, we have a5 and a4 over here, and a4 and a3 over there. Well, a4 is 3, and a3 is 2. Now, 1 times 3 plus 1 times 2 is 5, and 1 times 3 plus 0 times 2 is 3. So the numbers over here should be 5 and 3. And those are indeed the next pair of Fibonacci numbers, a5 and a4. Right. How does this help us to get a formula for an? We've just seen that we can get the pair of successive terms 5, 3 from the previous pair 3, 2 by multiplying by our matrix. But we can get to the pair 3, 2 from the previous pair 2, 1 by again multiplying by the matrix. And we can get to 2, 1 from 1, 1 in the same way. So we can express the pair 5, 3 in this way. Well, do we have to stop here? Can we in fact express the pair 1, 1 as the matrix times something else? Well, we can, and it's this. So, all in all, this gives us 5, 3 as the matrix to the power 4 times 1, 0. And it turns out that this is a better place to stop. Well, 0 wasn't in our original list, but we can always put it there if we define A0 to be 0. Now, remember which terms 5 and 3 were. 5 and 3 were the terms A5 and A4, so we can rewrite this equation in this way. So we've got the fact that A5, A4 is our matrix to the power 4 times 1, 0. And you can see that A6, A5 will be our matrix to the power 5 times 1, 0, and so on. In general, AN plus 1, AN, will be our matrix to the power n times 1, 0.
So summarizing the whole process as a network means we can express an plus 1 an in this form, as the nth power of this matrix operating on the column matrix 1, 0. Now, in order to find an explicit formula for an, what we want to do is to work out this nth power. But of course, you can guess how we're going to do that. We're going to do it by writing this matrix in the form q d q to the minus 1. So the first thing we have to do is to find the eigenvalues and eigenlines of our matrix. Phil?
And the way we do that is to solve the eigenvalue equation. That is, the determinant of this matrix with minus k's down the diagonal is equal to 0. Now, the determinant is 1 minus k times minus k minus 1 equals 0. So we have this equation. Now, that gives me k squared minus k minus 1 is equal to 0. Now, I can't see how to factorize that, so I'm going to use the formula. And the answer I get is the following. K equals 1 plus or minus the square root of 5 divided by 2. Now, it's going to be inconvenient to have those root 5s around, so I'm going to give these two numbers names. I'll call them alpha and beta. So alpha is 1 plus root 5 over 2, beta is 1 minus root 5 over 2. Now, if you've worked out these before the program, you'll know that alpha is approximately equal to 1.618, and beta is minus 0.618. And you'll have noticed that 0.618 appears in both of those. Well, all that means is that alpha plus beta is equal to 1. And you can see why that's true by looking at the formulas, because when we add these together, the root 5s cancel. So alpha plus beta is equal to 1. And similarly, looking at these formulas, we can see that alpha minus beta is equal to root 5. And we're going to use both these facts shortly. But the numbers alpha and beta have another interesting property. Let's see what happens if we multiply them together. Well, 1 plus root 5 times 1 minus root 5 is 1 minus 5, and that's minus 4. And 2 times 2 is 4. So alpha beta is equal to minus 1. So now we found the eigenvalues and some properties of them. What we want to do is to find the equations of the eigenlines. Now, we find the equation of the first eigenline using this expression. Our matrix times xy is equal to alpha x, alpha y. Well, that gives us two equations. X plus y equals alpha x, which we can rewrite as y equals alpha minus 1 times x. And from here, x is equal to alpha y. And we can rewrite that as y equals 1 over alpha x. Well, these two equations should in fact be the same, and we can see that that's the case by using our properties of the numbers alpha and beta. Because from the first property, we get that alpha minus 1 is equal to minus beta. And then from this last property, minus beta is equal to 1 over alpha. So in fact, both these equations are the same. Well, we can do exactly the same thing with beta instead of alpha. We find that the equation of the other eigenline is y equals 1 over beta x.
So now we know what the eigenvalues and the eigenlines are. Here's the eigenline corresponding to the eigenvalue alpha, and there's the eigenline corresponding to the eigenvalue beta. Now, what's the next stage in the process? What we have to do is to find a matrix Q which maps points on this axis to one eigenline and points on the other axis to the other eigenline. I'm going to choose a matrix Q which takes the point 1, 0 on the x-axis to the point 1, 1 over alpha immediately above it on this eigenline, and which takes the point 0, 1 on the y-axis to this point, 1, 1 over beta, on the other eigenline. That's quite a convenient point to have because it too has x-coordinate 1. And now Phil should be able to write down the matrix Q.
So we've chosen Q so that it maps this point to this point and this point to this point. So we know that Q must be this matrix, because this gives us the first column and this gives us the second column. What we want to do is to find the inverse of Q. And so the first thing we need to find is the determinant of Q. That is 1 over beta minus 1 over alpha. And we can rewrite this in the form alpha minus beta divided by alpha beta. Well, using the properties of alpha and beta, we find that this is just the same as minus root 5. Now, to find Q to the minus 1 from Q, what we do is to change these two terms over and make these two negative, and then we divide by the determinant of Q. And what we get is the following. Well, using the fact that 1 over beta is equal to minus alpha, I can rewrite this as alpha over root 5, and then 1 over root 5. And again, using the fact that minus 1 over alpha is equal to beta, here we have minus beta over root 5, and then here minus 1 over root 5. So now here's our matrix in the form Q, D, Q to the minus 1, with the eigenvalues alpha and beta down the diagonal. Well, the great thing about this representation is that it enables us to immediately write down the formula for our matrix to the power n, simply by raising alpha to the n and beta to the n. So now we're in a position to get our formula for an, because if you remember, an plus 1 and an were given by our matrix to the power n times 1, 0. Well, we've just worked out what this is. And we get the following. This is Q, this is d to the n, and this is Q to the minus 1. Well, to do a complicated calculation like this, we've got to work systematically, and I'm going to start calculating from the right. I'll multiply these two out. Well, in the top row, I get alpha over root 5, and in the bottom row, I'm going to get minus beta over root 5. Now, if I multiply these two together, in the top row, I'm going to get alpha to the n plus 1 over root 5, and in the bottom row, I'm going to get minus beta to the n plus 1 over root 5. Well, now, finally, I've got to multiply these two together, and I'm going to get in the top row alpha to the n plus 1 over root 5 minus beta to the n plus 1 over root 5, and in the bottom row, alpha to the n over root 5 and minus beta to the n over root 5. So now, looking at these terms, we've got a formula for an plus 1 and for an. So finally, we've arrived at what we wanted, which is a formula for an. An is alpha to the n minus beta to the n over root 5. Well, now remember what alpha and beta were. Alpha was 1 plus root 5 over 2, and beta was 1 minus root 5 over 2. Now that's rather a surprising result, because remember what an, the terms an are. An represents the number of pairs of rabbits in the nth month, and so an will always be an integer. And it's not at all clear that an expression of this form will always represent an integer. Well, we can make some interesting observations from this formula. Remember that beta was approximately minus 0.618, so its absolute value is less than 1. So beta to the power n will tend to 0 as n tends to infinity. And that means that when n gets large, the number an will be approximately equal to alpha to the n over root 5. Now you can check that in a particular case, and you'll find that that means that A12 is approximately 144.001 for 3 decimal places. And that's very close to the actual value, 144. Well, there's one further thing that we can get from this, and that is that the ratio of successive Fibonacci numbers is approximately alpha to the n plus 1 over root 5 divided by alpha to the n over root 5. And that, of course, is just alpha. So, as n tends to infinity, the ratio of successive Fibonacci numbers tends to alpha, which is about 1.618.
That result that Phil has just obtained about the ratio of successive terms in the Fibonacci sequence has an interesting geometrical interpretation. I've plotted on the graph all the points corresponding to the successive column matrices that we've had in our sequence. So I've taken an plus 1 as the x-coordinate and an as the y-coordinate of each of these points. Then by applying our matrix to any one of these points, we shall get the next point in the sequence. Now, how does the matrix act geometrically? Well, for points on this eigenline, it acts as a dilation with scale factor alpha. And alpha is a positive number, bigger than 1, which means that points get pushed out away from the origin. But what about the other eigenline? Points on this eigenline, the matrix acts as a dilation with scale factor beta. Now, beta is a negative number, and it's less than 1 in magnitude. So points on this eigenline jump to the other side of the origin, but they finish up closer to it. Points not on either eigenline feel both effects simultaneously. So suppose we look at the first point in our sequence and ask what happens to it when we apply the matrix to it. The effect of the dilation along this eigenline, that's the beta one, is to flip this past the origin, but I finish up closer to it. And then the dilation along the other eigenline takes me away from the origin, and so I finish up here. Then I can apply the matrix again, and the same happens. Flip past and along the eigenline, and again, and again. And very soon, look, I'm practically on the eigenline, and I continue along it. But the ratio of the x-coordinate to the y-coordinate of a point on this eigenline is just alpha. So this confirms that the ratio of an plus 1 to an gets rapidly closer and closer to alpha as n gets bigger. Now, the really interesting conclusion that we can draw from this argument is that the same result is true wherever we start. That is, if we take any pair of numbers and generate a sequence by using the Fibonacci rule, the ratio of successive terms in that sequence also gets closer and closer to alpha, because those initial values are represented by some point, say this point here. And of course we've got the same matrix, and it acts in the same way, just like this. And very soon I'm walking out along the eigenline.